So when setting up, let me do the quick introduction. So Simon Picard will be giving the last talk of the conference. So he's going to be discussing work that he did during his master several years ago before he fled into industry, works on AI, deep learning, data science, and the like. Let's give him a great experience so that he gets tempted to come back into our community and write more papers, give us more talks. Please, Simon.
Yes, many thanks for the introduction, Sanjoy. So yeah, it's an honor for me to close RTNS 2024 with my paper, which is my very first research paper. And this is a joint work with Antonio, Joel, and Gilles Gerhardt from the ULB. So our work... Okay. Yes. So our work is in the mixed-criticality system space. Those systems are systems where you have components with different criticality. And let me give you an example of such system. So imagine a car where you have an automated driving component and a passenger system component. What we want to ensure is that when we start the car, those two components, they work properly. And if at some point something goes wrong and we enter some abnormal condition, we still want to make sure that the automated driving component works properly, but we can discard the passenger entertainment system. This is a model that has been proposed by Vestal in 2007. And what we want to solve today is amongst all those systems, what are the systems that are schedulable with a given scheduler? Today, 17 years later, we cannot answer that question. We can have a subset of those systems looking at some sufficient condition, but what we will solve today is the exact schedulability test and answer that question of whether the system is schedulable with a given scheduler. So the model of this system, basically we have a task set, and the tasks, they are characterized by a criticality level, which is low or high. So we have two criticality level, hence the dual criticality system. We have a minimum interarrival time between the jobs that the task are releasing sporadically. So it's a sporadic system. And then the task have a relative deadline, and we have a worst case execution time per criticality level. So an estimate in the low mode or the normal mode, and an estimate in the high mode or the abnormal condition mode. In those systems, at each clock tick, what happens is that at first, the task can release potentially new jobs. Then the scheduler selects one of the jobs to be executed. That job is executed. And then upon the end of its execution, the job may signal its completion and declare that it has done all of the job that it has to compute. And that can lead to a potential criticality mode change, which is known as an overrun. And that basically happens when the job does not signal completion after having executed all its low criticality estimation. As you can see, there are several sources of non-determinism in this model. So namely, we have a potential job release that can or cannot happen, and we have a potential completion signal that can or cannot happen after each execution. And that then leads to multiple scenarios. So that means that when you start such system, there will be different scenarios that will happen every time you start it again. Let's look at an example of such scenario. So here we have a task set with a single task, a deadline of 3, a period of 4, a low estimate of 2, and a high estimate of 3. In this scenario, the task releases immediately its job. We can then compute the absolute deadline and the earliest next arrival time for the next job of the task. And then in this scenario, what happens is that the job is executed for 2 time units, and then it signals its completion. Here, it's important to understand that this signal could have happened 1 unit before or 1 unit after. So it's all of the values before the high execution time. So that's similar to having a B set of 1, if that's easier for you to understand. And then, given that model, what we then want to solve is this exact scheduling test. So given a task set and a scheduler, is it schedulable or not? In order to solve this problem, we are going to reduce it to an automaton safety check. This is an idea that has been explored by Baker and Crine in 2007 for multiprocessor sporadic single criticality tasks. That leads to a state enumeration and many states, so we will want to look at state space reduction technique. We will use a simulation relation, which has been proposed by Lindstrom in 2011, also for multiprocessor sporadic single criticality task. And we also propose a new approach with the oracle. And then we apply this whole framework to the sporadic dual criticality system. So let's look at how do we reduce this exact scheduling test to an automaton safety check. And in our automaton, we have states. We want the states to encapsulate all of the information of a specific scenario at a specific moment in time. So imagine we are in this scenario at the green arrow. The first thing that we want to recall is what is the current criticality of the system. So we start in the mode low, and once there is an overrun, it moves to the high mode. At that moment, there was no overrun, so we are in the low mode. Then we want to know for the task when it's the earliest next arrival time. So that's basically the number of time you need between the moment at which we are and the earliest next arrival time, so the half blue circle in this case. And then finally, we also want to recall for the task what is the remaining computing time for the current criticality. In this case, the job has been executed for 1 time unit. The low estimate is 2, so there is 1 time unit in the current criticality for that task. That leads us to our states where we recall those information. So that state, for example, is a state low 1, 3. So criticality is low, remaining computing time is 1, and the earliest next arrival time is 3. Now we can actually convert this full chronogram into a sequence of states that make a path actually. So at the very beginning, or at time origin, we are in this initial state where the criticality is in low. The remaining computing time is 0 because no job has been released yet. And the next arrival time is 0 because the task can release a job immediately. At the next clock tick, what happens? The task releases job. It is selected by the scheduler to be scheduled. It is then executed. So we take the initial estimate of 2. This is reduced by 1 because it is executed. And yeah, similar for the earliest next arrival time, which is 3. And we keep developing our path that way. Here you can see an important point of this approach is that the transition, they represent the elapsing of 1 unit of time in the system. Now we've been looking at a specific scenario. What we want to explore are all the potential scenarios given the task set, and see if any of them lead to a deadline miss. Those scenarios, they depend on the scheduler, which will select the job that can execute, and that job will have the possibility to signal its completion, so that's why it is important. And for this example, we will look at EDF with virtual deadline, which is a modification of EDF for mixed-criticality systems. So we start at the beginning of our chronogram. We are in this initial state, low 0, 0. And at the next clock tick, we can immediately arrive into 3 potential scenarios. Either the task does not release its job, and we remain in the same state. Or the task releases the job, it is scheduled and executed, and then the job signals completion. So you can see in the middle state, the first value is the remaining computing time, and it's 0 because it immediately signaled its completion. And the last one, it did not, so it still has 1 remaining computing time for the current criticality. And we keep looking at scenarios. Now we end up with those 6 potential scenarios only after 2 clock tick that will keep increase. And we end up into that kind of tree on the right side. Now, when we look at that tree, actually, there are some states that are repeated, and this is an important point of this approach, is that the values that are in the state are all relative. So we can actually group them. There is no notion of absolute time, and if you don't release and stay into this initial state, you just loop on the low 0, 0, 1, and you stay in that state as long as you want until you want to release a job. If we keep exploring this automaton, we end up with this picture. So let's take the time to look a bit at what's happening. So we start into the low mode. So what can happen? For example, the task releases job, it signals completion immediately. The next clock tick, we wait until we can release again. Then the task decides to be idle for a while. And then the task releases job, it is executed for one time unit, a second time unit, but does not signals completion. So we move into the high mode because we've executed 2 time units, which is the low estimate. And then we pass into the high part of the graph. And we can stay into this automaton forever. And that automaton then represents every single potential scenario until infinity of the task set with EDF VD. And in this automaton, it's a safe automaton. There is no deadline miss, there is no fail state, and therefore it is schedulable. Now, let's look at an unschedulable task set to see how we can detect it. Here we have another task set with 2 tasks, and that leads to a bigger automaton. But let's zoom on a specific path of that automaton representing a specific scenario to see what is this deadline miss. So this is the scenario. Basically, in this scenario, both tasks release their job immediately. There is no early completion, and EDFED schedules TO2 and then TO1 according to its logic. And when we are at the last state, so the red state, we are at a deadline miss, and we can see that by inspecting the value that we saved in the state. Basically, we are at the deadline that we compute from the next arrival time, and we still have some remaining computing time, so that is the definition of a deadline miss, at the deadline remaining computing time. And that concludes how we reduce this exact scheduling test to the automaton safety check. Now, this leads to many states. As we've seen here, with 1 task, we have some state. With 2, we have even more. That is going to grow exponentially on the number of tasks. So the first way that we look at to reduce the state space is to look at oracles. Oracles, they can tell us in advance, they can predict some events that allows us to modify our exploration and limit it. So here's the question: when we look at that path, when you look at that sequence of states that represent a specific scenario, the question is, can we predict the deadline miss? Can we anticipate the deadline miss? And we can. When we are at that purple state, we can check the laxity of the job, and we can see that it is negative. So the laxity is a very common necessary condition in the real-time community. And basically, we can see that we have 5 units of time to compute, but only 3 units of time until the deadline. So for sure, that will never work. That is then the concept of our oracles. It anticipates the deadline miss, it predicts it, and once we detect that there will for sure be a deadline miss, we don't need to keep developing our automaton. We can just stop and say, this is not schedulable, for sure there will be a deadline miss. This is an example of an oracle. We can have multiple oracles that are working together. Now the question again on this scenario, can we anticipate it earlier? And yes, we can. We propose to look at another necessary condition, which we call the worst laxity. And the worst laxity, basically it anticipates when we're in the low mode, what's going to happen in the high mode. So at the orange state, we can see that the laxity is 4. So we have 4 time unit of maneuver between until the deadline. But we can then also see that the task 1, it will need an extra 5 units of time of computation after the overrun. So then we can see that in total, we will have to execute 6 units of time, whereas we only have 5 units of time until the deadline. So that is a second oracle and gives a bit the idea that we can have many oracles working together to prune as much as possible the state space. Those approach, they enables us to reduce by 60% the amounts of visited state with a negative laxity and 68% with a negative worst laxity. Now, those figures, they are on unschedulable task set only because those oracles, they anticipate deadline miss. So if it's schedulable, there is no deadline miss and the amount of visited state is the same. This is my call for you to read the paper slide, where in the paper we also propose 2 other oracles that can reach 99% median visited space reduction. And that concludes the oracle way of reducing the state space. And now let's move to the simulation relation. So a simulation relationship, basically it's a relationship between states that has interesting property that I'm going to explain, of course. So let's understand what it is about and see this example graph. So here we have the state B that simulates the states C. In order for B to simulate C, it must have access to all the successors of C. So here, for example, C has access to F, so does B, so that is okay. You can see that the opposite is not true. B has access to D, C does not have access to D, that's why C does not simulate B in this condition. Now, it's also okay if B can access a state that simulates a successor of C. Here, for example, C has access to H, B does not have access to H, but it has access to G, which simulates H. So that also works. And then finally, the last criteria for the simulation relation in that relationship is that if a fail state is simulated, the state that simulates it must be also fail state. If we're able to prove that with that simulation relation, we can just avoid exploring the whole simulated part, because that ensures us that we'll reach the same outcome, and that outcome will be simulated by the successor of B, and therefore we don't need to go through the states of C. This is what we want to implement into our exact schedulability test automaton. So let's look here at those states. So we have the initial state low 0, 0 and low 0, 1. So low 0, 1, we can see that it has access to low 0, 0. And low 0, 0, it has access to itself. So does low 0, 0 has access to all the successor of low 0, 1? Well, yes, because it can access to itself. And so does low 0, 0, low 0, 1, sorry, has access to low 0, 0. Now we can look at low 0, 2. Low 0, 2 has access to low 0, 1. Low 0, 0 has access to itself, and we've established that it simulates low 0, 1. So low 0, 0 has access to a simulated state of low 0, 1, which is the only accessible state from low 0, 2. So we can see that low 0, 0 simulates both of those states. And when we inspect the values within the state, what is the difference between the state? Well, the criticality is the same. The task has no active jobs, but the next arrival time is sooner. If we look at another state where we have an active job, this does not work. And it also makes sense. When there is a scenario where I have less time until the deadline, I'm reducing the laxity, I'm probably not going to reach the same outcome as I would with that extra time. So our simulation relation is then works that way. We will say that one state simulates another if the criticality is the same, if the active tasks are identical, but the idle task can release sooner. So here you can see the next arrival time is smaller, and that's our simulation relation. When we apply it to our graph, we can see that we have several states that are simulated by some different states. And if we explore this graph with our relation simulation, we can avoid exploring them. So once we reach that simulated state, we say, this is simulated. I am guaranteed to reach all the same outcome with my simulating state, so I don't need to explore it. We've removed some state from the automaton. We've removed some transition. All of that translates to efficiency. In our experimental evaluation, what we've done is that we've explored some task sets with and without the idle task simulation, and then we report the execution time of those exploration. The scales are logarithmic, and what we can see typically is that with the idle task simulation, we are at one order of magnitude faster, or it takes one order of magnitude time in our exploration. So that's quite a strong state space reduction overall. And that then concludes our state space reduction technique. Now we can actually use our tool to assess the schedulability of schedulers. So what we've done, we've been looking at the EDF-VD sufficient test, and we plot the schedulability ratio for various task sets utilization. This is the curve. Now we can compare it with EDF-VD exact test, and here we can see the true power of the scheduler. We can also then quantify a bit the pessimism of the sufficient test and then see how far we are from the true power. What this also enables us is to test empirically some new schedulers. So we also propose the least worst laxity first scheduler, which is inspired by least laxity. And this is this concept that while we are still in the low mode, we anticipate what is going to happen in the high mode. And we can see that it gives quite some interesting performance, especially when we reach very high utilizations. And that then concludes our contribution. So in this paper, we've actually given an explicit model, formal semantic, for the sporadic dual criticality system. So that means that at every clock tick, we define exactly how the system behaves. This is actually a contribution in itself, because this this semantic is typically left implicit within papers, and so sometimes there can be some very small differences, but with eventually have a strong impact on the model. We've then used state space reduction technique with oracles that are fueled by the real-time community knowledge. We also implemented the simulation relationship, which is a strong formal verification technique. We are now able to find the true power of schedulers, which allows us to explore without pessimism and also do some scheduler empirical exploration. For this, we developed a tool in C++, which is open source, so you can define your scheduler and test it. And then finally, this whole framework is applicable to other models. This concept of the automaton safety check defining oracle simulation relationship. This is a general framework that is now formally proven and can be reused. And that then leads me to our future work. We would like to look at model extension with multiprocessor, varying CPU speed, preemption delays, and arbitrary deadline. We would also still like to enhance the scalability by defining new oracles, new simulation relation, and implement meta transition within our automaton. Then finally, we would also like to look at framework extension. We could, for example, look at solving feasibility by doing a game on the automaton where the decision is which job to schedule. Thank you for your attention.
Do you have any questions? So I had a couple, actually. The first was about this new algorithm you proposed. From the graph, it seemed to do a lot better than EDF-VD and also both the sufficient test and your exact test. But does it dominate? Do you have any? Is there a task system that EDF-VD exact can do that your algorithm will not do?
Yes, it can. So it does not dominate EDF-VD. Also, an important thing is that LWLF is dynamic priority. So that will lead to many switches. But it does not dominate it because there's some moment it looks only kind of at what's happening in high, and so sometimes it will be a bit obsessed with what's happening in high, and then the kind of the load in the low mode will be very high. So that means that the laxity in the low mode will be small when you look at tasks individually. But if you look at all the tasks together, you can kind of see that it won't work. So that's where EDF-VD does better sometimes.
Okay. So not anything else? Can I continue? Okay. No concerns if I continue, right? So why did you ask?
Yeah, thank you for a nice presentation. What do you mean by meta transitions?
Yes.
Meta transition would be to do jumps in the automaton. So here, one transition translates to one clock tick. For example, if we were to use a non-preemptible scheduler, we could do, hey, let's jump 7 transitions in one go. So that would be a meta transition.
So I had another question. So EDF-VD was designed the way it was because people didn't know how to schedule these. Your alternative scheduler is giving us some idea. Maybe this is another way to try. Can you imagine just searching the space, your transition graph to come up with an optimal strategy? In other words, it would be expensive, but in principle, it could be done, right? You could just do graph search to
Yes, that's the idea of this feasibility as the game on the automaton. So basically, at every state, like instead of giving the scheduler, you say, okay, there is one option is to schedule task 1, one option is to schedule task 2, and then you go into those different worlds, and eventually you look for a winning strategy where you don't have a deadline miss.
See, that's what you meant over there. Got it. Okay, so that would basically be an optimal algorithm. It would have bad running time because you have to do exploration every time, but
it would give you a scheduling assignment beforehand.
Please. Just a curiosity. So, what would be the size of the task set that you can handle with the review?
Yeah, we've been able to go up to 8 tasks. Here we have some experiment about the scalability. So we've managed to go up to 8 tasks, and there is a timeout of 15 minutes.
If not, thank you very much.
Thank you.